Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will be talking about the energy considerations of the particle kinematics. Specifically, we'll start with the topic of energy conservation. So we start with the topic in one dimension. So energy conservation in 1D. So what am I talking about? So the setup is that we have a particle. So suppose the particle P moves along the x-axis. The particle P moves along the x-axis under the force F acting in the positive direction. Right? So we have, again, the particle is experiencing a 1D motion, and for this sort of motion we have the work done by the particle is going to be F times V. The dot, there is no concept of dot in 1D, so F times V dt from time t1 to t2, right? And then we have that this is also equal to, from t1 to t2, f of x. Well, we are now going to change our integral from v to dx dt times dt, right? And this is f of x dx. Okay. Now the new integral is with respect to the variable x. So my new limits are from x1 to x2. So what we have found is, to begin with, our energy principle was as follows, what we saw in the previous module, that the change in the kinetic energy T2 minus T1 is equal to the work done by the particle, which is integral from x1 to x2 f of x dx. Okay. Now let us say a bit more, let us give a bit more information about this force F. Now suppose my force F is such that this is equal to the gradient of some scalar function, right? So suppose there exists a scalar function V whose gradient is this force, right? Or in 1D this is just the derivative with respect to x. So now if we plug this information in this integral, we are going to get that T2 minus T1 is equal to integral from x1 to x2 minus dv dx times dx, which is equal to v of x1 minus v of x1 minus v of x2. Okay. So in other words, if we rearrange all these terms, we are going to get that T2 plus V2 is equal to V1 plus T1. Okay. So what we have got is, so we call this scalar function as my potential energy. We just give a name to it, the potential energy. Okay. So what we find is that the kinetic energy plus the potential energy of the particle in state 2 is equal to the kinetic energy plus the potential energy of the particle in state 1. So which means that the net kinetic plus potential energy of the particle does not change. Let us call this constant to be the total energy of the system, or E. So E is a constant, and we have arrived at the law for energy conservation, and that happens if and only if F, the force F, satisfies this relation with the scalar potential function. Now when we have this constraint, we call F to be our conservative force field. Okay, and just to give an idea, this is not a very restricted class of fields. We will see almost all the fields that we have been discussing so far fall under this category. For example, the gravitational force is a conservative force field, or the spring force with the Hooke's law as the spring potential energy is also a conservative force. The examples for which the forces are not conservative are, for example, the frictional forces. Okay, so there are many forces appearing in real life examples which are conservative force fields. Okay, so so I think we have arrived at a very important conclusion with this very brief description, is that if we have a conservative force field, then the total energy is conserved. So for conservative force field, we have the idea of energy conservation. Okay, so that is what we have. So then let us quickly look at some of the examples we have been touching upon so far, and see what is the corresponding potential for these types of force fields. So for example, so we have we have the 1D SHM force field, and we have let us analyze some of these force fields. So 1D SHM force field and the 1D attractive inverse square force field. Okay, so we are talking about 1D SHM force field. Let's say we are talking about the spring mass system, right? The spring mass system, and in this case the force is coming because of the restoring potential of the spring. So the restoring force is given by minus alpha times x. So in the first case we have F is minus alpha x, and if we set it equal to minus dV dx, where V is my scalar potential, I can integrate this equation to get that my potential comes out to be half alpha x square. So my potential energy of the spring is half alpha x square. Okay, so then let us look at the inverse, the case for the attractive inverse square force field. So as the name suggests, in this case the force is given by k times x square. It is the inverse square force field, so 1 over x square, and it is also an attractive force field, so we put a minus sign. We assume that k is positive. So k is the constant of proportionality. So now if we set it up equal to minus dV dx, from here we can find that my potential is going to be plus k over x, right? So plus, or I think it will be minus. It is going to be minus k over x. Okay, so minus, and then we have an integration brings the minus. Okay, so potential is the minus k over x. Okay, so these are some quick examples. Let us look at the case of the projectile motion. So the problem says that a particle P is projected upwards with speed u, right? It is projected upward with speed u and the particle moves under uniform gravity, right? The particle moves under uniform gravity, and we need to find the max height. Find the max height and the speed. Find the max height and speed of the particle P when it returns when it returns to its starting point. Okay. This is the same problem, but we change the problem. We give a twist that we have to do this problem using energy conservation. So we redo this projectile problem using energy conservation. Okay, so for projectile motion, we know that the net force acting on the particle is minus mg, and if we set it equal to minus dv dz, well, z is the vertical direction in which the motion is happening. We see that the potential comes out to be mgz, right? So we have found a scalar potential, which means that the force field is conservative, and we can say from energy conservation that half mv square, the kinetic energy, plus mgz is equal to a constant which is E. Now, how to find this constant E? Notice that at t equal to 0, the particle is being projected with speed upwards. So our velocity is u, and at t equal to 0, the distance covered is 0, the height is 0. So we plug all this information and we find that E is half m u square, plus there is no net potential energy, so that is 0. So from here we find an equation, this one, we find an equation, and from here we see that we get mv square plus 2 mgz is equal to mu square. We cancel out all these m's, and now we have an equation for the velocity v, which is u square minus 2gz, v square. So we have to find the max height. Now we need to find from the problem says we need to find the max height and the speed when it returns to its starting point, right? Now at maximum height, we all understand that the particle will stop. So the particle will go, reach the maximum height, stop, and then come back. So at max height, v square is 0, or we get that u square is equal to 2gz, right? Or we see that z is u square by 2g. Z is u square by 2g, and that is our max height. That matches with our relation that we found using the Newton's second law of force balance, right? And now then we also have to find the speed of the particle when it returns to its starting point. Well, we can directly use the energy conservation, that so using the energy conservation, we have v square is u square minus 2gz. So when at t equal to 0, the speed was u, and at the time when the particle returns to its starting point is the time when z is 0. So we have z is 0, which means that we get v is equal to u, or we get v is equal to u. So the speed is the same speed with which the particle started moving upward, right? So we see that using energy consideration, the problem becomes very quick and simple. So let us now look at a few more examples and try to solve it using energy considerations. So the problem says a particle of mass m is projected from a point x equal to a with speed u, and moves along the x-axis, under the simple harmonic motion, force field F is equal to minus m omega square x. Okay. So we need to find the maximum distance from the origin O and the maximum speed of the particle. So find the maximum distance, max distance and max speed from the origin. Okay, and again, without saying, we will try and do this problem using energy consideration. So using this force field, we can find the potential. So minus dV dx is equal to minus m omega square x, and we see that the potential comes out to be half m omega square x square. Okay, so that's my potential energy. So what we have is, now the particle of mass m is projected. So now my energy conservation principle is, the energy conservation principle comes out to be the sum of the kinetic energy half m x dot square plus the potential energy half m omega square x square is a constant E, and this E will be found using my initial condition. So at x equal to a, E will be half m omega square a square, and the speed is u, so this will be plus half m u square, right? And so then we can quickly write down the equation of motion here. The equation of motion from the energy principle, we find that this is equal to x dot square is equal to plus omega square x square is equal to omega square a square plus u square. So that is my energy principle. So from here we can quickly find the two quantities that we were trying to find, namely the max distance and the speed from the origin. The max distance will be the case when the speed becomes 0, right? So max distance happens, the max distance from the origin is at the time when the speed becomes 0, and we find that from this case x comes out to be omega a whole square plus u square by omega square square root, right? There will be two values, plus and minus, because the particle is experiencing an SHM, which means that it can achieve a max distance either side of the origin, right? And then we have to find the max speed. The max speed is when the distance from the origin is 0, or the distance is 0. When x is 0, we find the max speed. In that case, the max speed comes out to be very quickly, which is V max is square root omega square a square plus u square, and also with a plus minus sign, which means that on either side of the origin, whether it is on the left, it will have either a plus, and if it is on the right, then it will have a minus, and vice versa. It could be, it all depends in which direction the particle is traveling. So hence the plus minus. But well, we need to find the max speed, so let me keep an absolute value. So I remove this plus minus. Okay, so this was very quick way of solving the problem. Now let us look at the general scenario of a potential problems which have a scalar potential. Okay, so what I am trying to show are the general features of conservative 1D fields, of conservative 1D motion. Okay, so what we see is, typically when we talk about conservative motion, we expect that there will be a scalar potential which governs the potential energy of the system, right? So typically my scalar potential, so if I draw the energy diagram is the total energy versus, let's say, the position, right? And let's say the energy of the system is at a particular level. Let's say, of course, the energy of the system is conserved, so it will be having some fixed value, let's say E naught. Now in this case, we have that this E naught is, let's say, this is going to be the following. This is Now what I am trying to draw here is the potential curve V of x, right? So this is going to be the following: V of x, and then what we see is that the total energy of the system is conserved, of the particle under motion is conserved, and if this is the potential energy, we expect that the particle, let me let me identify some of the points. This first point, when the potential energy curve hits E naught, is A, the second point is B, and the third point is C, right? Now remember that the total energy of the system is always E naught. So total energy, which means I cannot go and in a region above this this straight line E naught. Why? Because the total energy of the particle is fixed, which means that given this potential curve Vx, the particle is either going to lie in this region which I am shading, or it is going to lie in this second region which I am shading, right? So what it shows is that in the first region, the particle is as if it stays in some sort of a trapped region, right? So if the particle is here at, let's say, point A, x equal to A, it will have typically a velocity towards the right, and if it, why? Because it cannot have a velocity towards the left, because otherwise it will overshoot the total energy E naught. So that is not possible. And then similarly, when it reaches the point B, it will have a speed towards the left, otherwise it is going to overshoot this curve E naught, right? So which means that the particle is going to, once disturbed from some of its position here, the particle is going to go round and round inside this well, or what we call as the particle experiences a periodic oscillation. A periodic oscillation. Okay. So this happens typically near the minima of the potential. Now on the other end, if we are on the second shaded region, there is no minima of the potential here, and the particle is going to continue its motion without periodicity. It may not reach back its original starting point because there is no minima of the potential, right? And so we call this typically the energy can even extend to the negative plane, right? So it can continuously go down, the potential can continue. So the particle, as if the particle falls in this deep well with no minima, right? And we expect as it falls deeper and deeper, the velocity or the kinetic energy of the particle is going to increase, right? Okay, so this is not the case of a periodic motion in this second region. Okay, so let me call this as region number 1, and let me call this as region number 2. So what we see is in region 1, we see that the equation of motion, using our let me assume that the mass of the particle is 1, mass m is 1, right? So now the equation of motion is dx dt, so half mv square, so half 1 times dx dt whole square plus, so that is the kinetic energy plus the potential energy is equal to E. So we get that dx dt is equal to square root E minus V of x, and we get that this is E naught, and this will have a positive sign because, well, there is a half also, this will be 2 times E naught minus V. So we have a positive sign, and with this we can find the position of the particle given our E naught and the potential energy curve Vx, right? From here, if we integrate out, and we can immediately find what is the period of oscillation. This is going to be integral dx by square root 2 times E naught minus Vx, and from here we can find, so this will be from the period of oscillation will be from x equal to a to x equal to b, right? And this will be twice of this value because it has to come back. So we can immediately find the period of oscillation. Okay, and then similarly in region 2, we find that dx dt is going to be, again using energy consideration, we find that this is going to be the minus, the other one, minus 2 times E naught minus V, the minus sign. The minus sign because it seems that the potential energy continuously decreases, right? And there is, we cannot expect that there will be a period of this motion in region 2. Okay, so that completes our general scenario of the case of 1D motion of a particle with conservative fields, right? So now let me conclude this brief discussion with one example, and then we are going to conclude this module. So what we have is, okay, so what we have is, we have a particle P of mass 2 which moves on the positive x-axis, right, which moves on the positive x-axis under the force field, F is equal to 4 by x square minus 1, right. So what we have is, initially we get that P is released from rest at x equal to 4, and so this is my initial data. It's released from rest at x equal to 4, and we need to find the extreme points, and period of oscillation, period of the motion or oscillation. Okay. So what we have is, we already know that this is a conservative force field. If we can find a scalar potential, we integrate. So to begin with, we integrate, find the potential, minus dV dx is 4 by x square minus 1, and we find that my potential comes out to be 4 by x plus x. Okay, so what we have is the following. My potential is the following, and I can write down my energy conservation as half the mass is 2 times x dot square plus the V, the potential is 4 by x plus x, right, and this is equal to capital E, and E is found from the initial data. The particle is released from rest. So we have x dot is 0, and it is released at x equal to 4. So E comes out to be 0 plus 5. So 4 by 4 plus 4, it gives you 5. So my constant E is 5, and my equation of motion is the following from the energy consideration. So x dot square plus 4 by x plus x is equal to 5. So from here I can quickly find, well, we need to first find the extreme points, right? The extreme points are when x dot, the V is 0, and from here we can find what we need to find, the extreme points. We solve this equation, 4 by x plus x is equal to 5, and we are going to get x is equal to 4 and 1. Okay. So once we have the extreme points, we have to find the periods. The period will be the particle is oscillating between its extreme points A and B. So the period t will be integral. Well, we look at this equation. From here we can immediately deduce what is the total time taken to travel between the extreme points. Dx dt is equal to 5 minus 4 by x plus x, and we see that this is also equal to 2 times t is equal to 2 times 1 to 4 integral from x divided by x minus 1 times 4 minus x. Okay, so this is after simplification. So we have put a 2 because the motion has to be twice the distance traveled between the extreme points, and that gives us the period roughly. The integration gives us this value.